When most people talk about elasticity, they picture something like a rubber band that easily stretches out of its original shape. But in physics, elasticity describes the exact opposite behavior. It is a strict measure of how perfectly a material recovers its original geometry once an external force is removed. Because of that strict condition, a solid steel bridge cable is vastly more elastic than a rubber band. True elasticity requires intense internal restoring forces. When a force separates the atomic lattice of a strong metal, the bonds act like incredibly stiff springs, aggressively pulling the atoms back to their exact resting configuration. Those microscopic, invisible restoring forces are the only thing keeping towering macroscopic structures standing under their own weight. To design safe buildings, build complex machines, and construct massive infrastructure, engineers cannot rely on subjective ideas like stretchiness. They need a precise geometric language. They need a unified mathematical model that tracks exactly how external forces flow through a material, store energy in those atomic springs, and eventually sever the bonds completely. Measuring the raw pounds of force applied to an object, or its total physical stretch in inches, is mathematically useless. The raw numbers change based on the object's thickness or initial length. This diagram maps the solution. First, we define stress as the applied force divided by the cross-sectional area of the material. Next, strain is the newly added length divided by the original starting length. Because strain is a ratio of two lengths, it is completely dimensionless. This provides a universal metric to compare the behavior of any two materials, whether it's a microscopic copper wire or a massive steel I-beam. And when you apply small deformations to a solid, a clear relationship emerges, known as Hooke's law. Stress is directly proportional to strain. The constant of proportionality is the modulus of elasticity, representing the strict straight-line relationship. Stretching that material requires physical work to overcome the strength of the atomic bonds. That work is stored inside the material as elastic potential energy, calculated as exactly 1/2 the product of the stress, the strain, and the total volume. This stored energy is the exact mechanical engine that violently snaps the solid back to its original shape the moment the external force is removed. Normalizing force and deformation into stress and strain gives us the universal language we need to map how any material on Earth stores and releases that energy. Plotting stress against strain creates a topological curve that functions as a physical DNA for any given material. Looking at this stress-strain curve, we start at the origin and draw a perfectly straight line upward to point A. This is the elastic region. If we remove the stress, the material travels perfectly back down this line to its original shape. Moving from point A to point B, Hooke's law breaks down. The line is no longer straight, but the material can still theoretically recover its geometry. Point B is the ultimate structural threshold, the yield point. At this exact coordinate, the external stress permanently overpowers the internal restoring forces of the atomic lattice. This marks the onset of plasticity. Crossing the yield point guarantees permanent deformation. The material is compromised and will never return to its original shape. If we continue to increase the strain, the curve arcs upward to its highest peak, point D. This is the ultimate strength. It represents the absolute maximum stress the physical structure withstands before it begins to dangerously thin out, known as necking. Past the ultimate strength, the material rapidly fails, illustrated by this sudden drop to point E. This is point E, the fracture point. The atomic bonds sever completely, and the solid aggressively breaks in half. From skyscrapers to airplane wings, safe structural engineering strictly operates inside that narrow, straight-line region from O to A. Crossing the yield point is avoided at all costs. Real-world engineering is rarely as simple as pulling a wire in a straight line. Materials are twisted, sheared, and crushed from multiple directions simultaneously. Because of this, a solid's modulus of elasticity changes based on the specific geometry of the applied force. This three-panel diagram maps the directional moduli. On the left, Young's modulus measures resistance to linear stretching or compression. Heavy, load-bearing structural metals possess a massive Young's modulus. In the middle, the shear modulus tracks resistance to horizontal sliding. On the right, the bulk modulus measures resistance to volumetric compression when uniform pressure crushes an object from all sides. Comparing states of matter, solids possess the highest bulk modulus. Liquids are only slightly compressible, while gases compress easily. But pushing or pulling a solid along these directional axes triggers a hidden dimensional consequence. To account for it, engineers rely on Poisson's ratio. This animation of Poisson's ratio shows the physical reality of stretching. Mathematically, as the wire elongates through longitudinal strain, it must simultaneously become thinner, creating lateral strain. The exact ratio of this thinning depends purely on the innate atomic properties of the material itself, regardless of whether you're stretching a small pipe or a massive structural column. By combining the directional moduli with Poisson's ratio, engineers construct a complete 3D mathematical toolset. They can predict exactly how a solid will deform under any complex combination of real-world forces. When we take these microscopic models out of the lab, they define the sheer physical scale of the natural world. It raises a simple constraint question: why don't mountains grow infinitely tall? As a mountain gains mass, gravity pulls millions of tons of rock downward, creating immense compressive stress accumulating at the very bottom. Looking at this cross-section diagram, we see the geologic limit connects directly to our stress-strain curve. A mountain can only grow as high as the compressive stress at its base remains below the yield point of the underlying bedrock. If the sheer weight of the rock crosses that yield point, plasticity takes over. The bedrock physically flows or shatters, and the mountain sinks back down into the crust. This exact same mechanical constraint governs human engineering. It dictates the maximum payload of an industrial crane and the exact diameter required for suspension bridge cables to hold steady over a roaring river. Whether formed by millions of years of plate tectonics or forged in a steel mill, all solid structures are bound by the invisible rules of restoring forces. Ultimate physical safety is simply the strict mathematical enforcement of the elastic limit.